Today we will first begin with the advantages of the sinusoidal quantities, that why it is more appropriate. So use of the sinusoidal voltages applied to appropriately designed coils results in the revolving magnetic field which has the capacity to do work. Okay. So when the sinusoidal voltage is applied, a revolving magnetic field is developed. Okay, so as we have discussed in the previous class also, that there is a relative motion between the electric field and the magnetic field. So when we are talking of large generators, AC generators, which are the alternators, magnetic field is revolving. Okay, so that is due to the application of sinusoidal voltage. So the waveform from the generation to utilization remains same if the sinusoidal waveform is generated. Okay. So when we are talking of the applications of the sinusoidal voltage, it is generated in the alternators in a sinusoidal manner. Then, as I have discussed earlier, that the generating voltage is somewhere around 11 kV. Okay, but the voltage which we use as a end result in our loads is 230 volts. Okay, so there is a mismatch. So what needs to be done? First of all, the generating stations are not near to us, or you can say that it is not near to the load centers. Okay, so first of all, transmission of the voltage is to be done. So whenever the transmission of the voltage is to be done, then its magnitude is increased. If the voltage is generated is 11 kV, it is its magnitude is increased using step up transformers at the substations. Okay, so then this voltage is transmitted to different cities which act as a load centers. Okay, so but the requirement is such that the waveform, the sinusoidal waveform should not get distorted. So we can say that by and large the waveform of the generation, waveform from the generated sinusoidal voltage to what we receive at the load end remains same, although there are harmonics due to different kinds of loads it caters. Especially the harmonics are developed due to the presence of inductive load. Okay, for example, this is the instantaneous EMF and this is the ideal AC volt, but we can get some distortion. Okay, but still we can say that it is wave shape is same and it is better than the other waveforms. Okay, so it is advantage to use the sinusoidal voltage or sinusoidal quantities. And third point is there is no oscillations in developed torque and absence of noise in operation. Okay, again, this is a bit controversial because, as I have just mentioned, that there may be oscillations and there are noise as well, depending upon the rating of the load. Okay, for example, if we are using laptop using the AC supply, we do not get any oscillations, we do not get any noise. But if we are operating the same AC for motors, induction motors, especially which are reciprocating in nature, okay, and there is air gap involved, then some noise is produced. Okay, non-sinusoidal voltages which contain harmonic frequencies are harmful to the system. Okay, so which are the non-sinusoidal quantities? It can be square wave, it can be triangular wave, which are not obeying the sine wave shape. So they are categorized under this. So what happens that there is increased losses in generators, motors, transformers, transmission and distribution systems. More interference is there to nearby communication systems. Okay. Sometime we see that the distribution lines, distribution power lines, and telecommunication lines, especially in earlier days when we used to have landline phones, then we could easily see that there is the interference of these power lines to nearby communications systems, and some noise is also produced. So while we are talking on the landline, it is not, we cannot communicate easily. Okay, so resonance may result in the over voltage or over current from generating station to consumers premises, and it may damage the equipments and increase losses. Okay, so if the quantities are non-sinusoidal and at resonance, its voltage may peak or its current may peak, so at that time it may harm the equipments. Increased current through power factor improvement capacitors. So in the non-sinusoidal quantities, the power factor is also less. So if we involve the power factor improvement capacitors, there it may result in increased currents. So these are some disadvantages if the non-sinusoidal AC voltages are used. Okay. So also the misconception should be clear that the every AC voltage is not sinusoidal voltage. Okay, AC supply may be there, but it may be square wave, triangular wave, etc. as well. Okay, so it is a slight difference in the wave shape. So angular velocity you know very well. Next is the electrical degrees and mechanical degrees. So what is the difference between these electrical degrees and mechanical degrees? So if we are having the two pole machine, so this is say north pole and this is south pole. So the angle between them is 180 degree. Okay, so mechanical angle is the actual angle which is between the two poles, so it is 180 degrees. Here electrical angle is also 180 degrees. Electrical angle between the alternative poles are always 180 degrees. Okay, so so far this is good enough. But if we move on to four pole machine or six pole machine, then things change. So how do they change? Let us see. So this is the four pole machine. Okay. So let us assign this as North Pole, and there are three more poles, say A, B, C, etc. Okay. So here we can see that the alternative poles, these are the neighborhood poles of North Pole. So they are South Poles, and similarly again these are the neighborhood poles of North Poles and these are South Poles. Okay. So main reason of this arrangement is that the flux lines or the magnetic lines of forces travel from North Pole to South Pole. Okay, this is universal fact. So we do not want them to follow the bigger path. Okay, so this is the main reason that if the South Pole is in vicinity, is in neighborhood with the North Pole, so these lines, these magnetic lines of forces or flux can travel to the desired path easily. Okay, there is no losses, and when this is there is a armature or rotor in the center. When it is rotating, it will cut these flux lines, and by d phi by dt EMF will be produced. Electrical degrees remains 180 degrees. So here there is a 180-degree angle, electrical angle, but the mechanical angle will be 90 degrees. Here between the North Pole and the South Pole, it is again 180 degrees, 180 degrees, 180 degrees, and so on. Okay, so this is the difference between the mechanical angle and the electrical angle and the arrangement of the poles. So next is our RMS or effective value. RMS value is also called the effective value of alternating current. So it is the root mean square value, root mean square value of the alternating current. But while calculating, what we do, This is RMS, but in actual, what we do, we will square first, then take mean, then take root. Okay, so it is root mean square, but it follow the reverse trend. Okay, so what actually is this RMS current? So the RMS value of the alternating current or the voltage is given by the steady current or the voltage which, when flows or applied to a given resistance for a given time, produces the same amount of the heat as when the direct current is flowing or voltage is applied to the same resistance. Okay, so what does that mean? So we have observed that since it is a alternating current, sinusoidal current, so the instantaneous EMF, which is the EMF at any instant, instantaneous current, which is the current at any instant, it keeps on changing. Okay, so we are in not in good position to say what is the current at a particular instant which is being served to a load, lamp load or fan load, etc., because it is changing. So we are required to designate a constant value that is called the RMS value. So that RMS value will produce the same amount of the heat. So what is heat? You know, heat is the I square RT. Okay. So if the current is DC current, then there is no problem because DC has the fixed value. So when this amount of current is passed to a resistance for at any time, say T, it will produce a particular heat. Okay. So if we replace this changing or instantaneous current by a fixed value, which will produce the same amount of heat as this DC current, then RMS current is that current is called RMS current. Okay, so now let's formulate it. So this is the waveform of the current. So we have to take the while calculating the RMS value I have just mentioned. First of all, we have to take the square, then mean, then root. Okay, so this current, now we are calculating the RMS or the effective value of the alternating current. We are not calculating for the sinusoidal current. Okay, so there is a bit difference. Alternating current is that current which repeats itself after the passage of a particular time or degree. Okay, so it may have the sinusoidal wave shape, but it may not have the sinusoidal shape. Okay, so every this alternating current can be plotted as a curve only if it is defined as a function. Okay. For example, if we are talking this alternative current as sine omega t, okay, this this function can be current Im sine omega t or EMF Em sine omega t. Okay, that is good enough. So if the function is clearly defined, we can square that function, no problem. And also we can plot that function. But if the function is not defined or irregular, then what to do? Because if the function is clearly defined, then we can, for example, if there is any function uh, whose RMS value is to be taken, then that is clearly defined. It can be squared and its mean can be taken. So how do we take the mean value of a defined function? We can take the area under the curve. We can take the integration to calculate the area under the curve, which you have studied in your previous class +2. Okay. So in this way, we can take the mean value and then we can take the root to know the RMS value. It is good enough. But if the function is not defined, so it cannot be clearly plotted on the XY graph. And similarly, the mean cannot be taken easily. Okay. For example, if we say that your class is having 30 students and we are required to calculate the mean value of the weight. So can we define the mean by a function? No, we cannot, huh? Or we can do so. For example, you can say that the person who is having least weight in your class is say 45 kg. Okay. And the student which is having heaviest weight in your class is 70 kg. Okay. So whenever there is a such type of situation that a group of values cannot be defined by the function, then what we can do, we can take the individual values of all the its constituents and then take the mean. Okay, then we can take the mean. So same we will do here. So let us suppose that this waveform is having the currents and that current can be divided into say I1, I2, I3 till In. So each of these components will produce some heat. So I1 will produce the heat I1 square RT T upon N. Similarly, the heat produced by the second current I2 will be this and so on. The current produced with the by the nth component of the current. Okay. So we are now in position to get the total amount of the heat produced in this non-uniform waveform. Okay, so this is the total sum of the heat produced. So heat is in the form of energy or power. So if we are going to multiply by time, it becomes energy. So its unit is joules. So going by the definition, this heat produced will be equal to that fixed amount of the heat which is produced by its RMS current value. Okay, so we have equated these two equations, and these RT and RT gets cancelled out, and this square component is replaced by this square root. So we get this value as the RMS value of the current. Okay, so this is for the alternating quantity whose time period is given, and it is the uniform. It can be plotted in the form of the function, and this is for the non-uniform. Next topic is the average value of the sinusoidal current and voltage. So we know that the sinusoidal current or the voltage or the sinusoidal waveform is uniform in nature. So it is having the positive half and the negative half. So if we take the average of a sinusoidal quantity over the whole period, it becomes zero. Okay, because this wave shape, positive wave shape, is equal to negative wave shape, so it becomes zero. Here's a result from YouTube. Okay, so but our concern is not to take the average value of the complete cycle. We are focused on the positive half cycle. Okay, so if the some numerical or the question comes for this type of situation, so you should be aware of that whether we are talking of the whole cycle or the positive half cycle. Okay, so if we are talking of the positive half cycle, the average value will be taken as area of the first half cycle upon pi, because the time period, the angle in radians is pi. So area of the half cycle is taken, and this is the our instantaneous value I. So I d omega t, and we substitute this value I m sin omega t, then integrate it. So when we integrate, sin omega t becomes minus cos omega t. We apply the limits pi to 0, 0 to pi, and take the mean 1 upon pi to get the average value as 2 im by pi. Okay, so this is for current. Similarly, if we are replacing this current by EMF or voltage, same results will be produced. Okay.